Everybody, welcome to Lecture 7 of Graphical Models and everything else that we've been talking about, advanced inference. A course isn't good unless it has the title, unless it has the word advanced in it, right? So that means that this course is a nice class. So, or a good one. A couple of announcements before we begin. One is just a reminder to everybody that homework 1 is due on Tuesday, which happens to be tomorrow night at 11:45 p.m. Hopefully, you've all had a chance to start it and maybe even finish it. Could I just have a show of hands? Who has started the homework? Oh, very good. And who has finished the homework? Who has not started the homework? Oh, okay. So those of you, that small percentage of you who have not started the homework, please start right after this class, but not during the class, after the class. So today we're going to be continuing our discussion of junction trees and relate junction trees to what I think is a very interesting, purely graph theoretic construct called intersection graphs. But you might think, well, why are we defining intersection graphs? Well, intersection graphs are, it turns out, can define junction trees in a way that I think imparts to them a very, very strong intuition. So we'll spend a bit of time on intersection graphs. And then if we have time today, we'll probably start talking about inference on junction trees. But chances are that will be on Wednesday's lecture. So just as a review, a couple of definitions and concepts that we talked about last time, including the idea of a decomposition of a graph, G, where, if you remember, basically we say that a decomposition exists if there's a separator S, or I guess in this case it's the separator C, that separates A and B, and it has to be that the separator is a clique, meaning it's complete. And then the second definition is this notion of decomposable. A graph is decomposable if G is either a clique or if G possesses a proper decomposition, which means that the left side and the right side truly yield a smaller graph as you go down. And it has to be the case that both the left-hand side and the right-hand side are themselves decomposable. So it's a recursive definition. And it basically meant the following, that we can essentially write if we have a decomposable graph, if the graph is decomposable, what that means is that if we have any probability distribution which is in the family corresponding to this graph, according to the standard Markov property, the one that we've been using, this factorization property, or there are a number of others which we didn't really talk about, that basically means that we can write the probability distribution as a numerator and a denominator, where the numerator consists of marginals, which we saw correspond to max cliques in the graph, and then the denominator corresponds to separators. And in fact, the general form of the factorization has this form, and this is really important, where we take the product of the cliques, and these are clique marginals, and the denominator is the product of the separator marginals, where the separator marginals might be used multiple times, depending on this idea called D of S, which is the shattering coefficient, which is the number of connected components that a separator breaks the graph into. And the shattering coefficient is really important. So why is this important? And we're going to see when we talk about inference, which is the third section in today's lecture, which I just said we probably won't get to today. But the reason why this is important and why this expression is important, because when the graph is decomposable, which we know also to correspond to the triangulated models, we can write the joint distribution, P of x, in this way as follows. Now what we can do then is we could start out with a product of factors in the numerator and the denominator, which aren't necessarily marginals. But if we do some manipulation to those factors in the form of message passings, what we can at least possibly get to is where those factors do indeed correspond to clique marginals. Now by clique marginals, I mean that these are actually truly locally normalized marginals. Probability of x of c, that's basically the marginal. That's like if you sum out all of the variables except for c, what from this thing over here, then what you get is x of c. Okay, so that basically gives us the marginals, and once we have these marginals, then we can do all of the things that we want to do. For example, for learning distributions. Okay, but we also saw examples that were not decomposable, like the 4 cycle. A couple of propositions that we proved. All of the max cliques of a graph lie in the leaf nodes of the binary decomposition tree. Remember, what a binary decomposition tree is this thing here. Remember that guy? Here's the binary decomposition tree. We're using yellow now instead of purple. Secondly, the necessarily unique set of all minimal separators in the graph are included in the non-leaf nodes of the binary decomposition tree, and the number of times that these separators occur, is 1 less than the shattering coefficient. So getting back to here, do we have, I guess the shattering coefficient here in each case is 2. So the separators don't occur more than once in the denominator. But in general, they occur more than once if it's the case that the shattering coefficient is more than 2. And then we also proved that a given graph is triangulated if and only if it's decomposable. So that basically means that the triangulated graphs, the things that are a consequence of elimination, are also the graphs that we can actually write the probability distribution according to this numerator and denominator set of marginals. We also defined a tree decomposition, which is basically a tree. Here's the tree part. The nodes of the tree correspond to clusters in the original graph, and the edges in the tree correspond to edges in that tree. And the tree decomposition has to have the property that it's both a node cover, meaning that if we union together all of the clusters, we include every node. So that means every node is included at least once in a cluster. It's also an edge cover, which means that any edge in the original graph has to be included in some of the clusters, one of the clusters. And then thirdly, that when we take any vertex, any node in the original graph vertex, which is this thing here, that basically if we look at in some sense that you could think of it as the forest, the potential forest in that tree, it's actually not a forest, it's a tree. It's actually connected. It forms a connected subtree. And that, in some sense, to say connected subtree is a little bit redundant. So we just really mean it's a tree. Okay. We defined a cluster graph, which is basically a graph of clusters where there's an edge whenever there's a non-A and B intersection. We defined a cluster tree where we drop the requirement for there to be an edge if there's an intersection, and we just say it's a cluster. It's a cluster where the vertices of the tree are clusters, and it's a tree. And then importantly, we define the cluster intersection property, where we're given a cluster tree. This is an important definition to remember. And if we take any two nodes in the cluster tree, which remember consists of two clusters from the original graph vertices, then the cluster intersection property states that if we take the intersection of those two clusters, which is these things, then that intersection lives in the path along the tree. And let me just draw a picture in case this isn't clear. So here's a tree where each one of these nodes here are a cluster of original graphs. And if I were to take, for example, say this guy and maybe this guy, then it would necessarily mean that along this path, there's a unique path. That means the intersection of the purple and the red have to live in every single one of the nodes in the orange path, which consists of, there's only two of them here, that one and that one. Yep, question?
For any possible of these drawings, or just needs to be one for it to hold the tree?
Sorry, I didn't quite...
So is it there exists a C1 or C2, or is it for any C1 or C2 you could pick?
So it says for any two clusters in the tree. So it means for all pairs. For all pairs. So any two pairs you choose, for all pairs, for any pairs, definitely you are guaranteed, because it's a tree, that there's a unique path between any two pairs. I always say deliberately that the, quote, necessarily unique path, because it's a tree, it's necessarily unique. So it's a necessarily unique path between any two clusters, and any one of the nodes on that unique path has to essentially be larger than or equal to the intersection of the two pairs of clusters that we chose, which define the path. Okay? The running intersection property, which some people have a little bit of trouble with at first, and so we had a couple of nice pictures of it, but basically it says the following. So the running intersection properties, we're starting with a set of subsets. So we're not even necessarily talking about a tree, but it really does define a tree. So we have a set of subsets, or a set of clusters of the vertices of the original graph, and it's an ordered set of subsets, so there's a particular order to them. And it satisfies the running intersection property, or what's sometimes called the RIP property, if it is the case that for every position in that order, the intersection of that cluster and the whole history, everything that comes before it, the union of everything that comes before it, is sort of summarized by the intersection of that cluster and some particular cluster in that order before it. So that basically means that for all I, that's every position, there exists some previous cluster such that the intersection of the current cluster and the whole history is equal to the intersection of the current cluster and that pre-designated, that specific cluster. So that means that that cluster J acts as a representative of the history, and then it's defined in terms of clusters of nodes in the graphs. But you can sort of see that because you're always, think about remember the definition of the tree. We had all these different equivalent definitions. That bottom one was this generative one, where we always add a new node and connect it to one previous node, and a new node and connect it to one previous node. And when we generate a graph that way, we always get a tree. And so in some sense, you can see that the running intersection property always generates a tree for us. Okay. And we can also say that the running intersection property holds on an unordered set of clusters if such an ordering can be found. That's just a notational convenience. So here's a little bit of a expansion of that. This is again from a review. So we have this ordering C1 through CL. We can define the history at position I is the union of all of the clusters up to position I. Is that a question or just a stretch? It's a stretch. Yeah, you're not allowed to stretch in this class unless you ask a question. So there's the residual or the new stuff. This is the stuff that's in the cluster that's not in anywhere in the history. And then there's sort of the separation or the non-innovation or the intersection, which is basically the commonality between the current cluster CI and the whole history. And we can, of course, recreate the current cluster, which is the residual. The residual and the separator are non-intersecting, but they partition the new cluster C. And so what the running intersection property says is that this is the current guy, and he's connected by this edge to some sort of representative Cj, which is such that the intersection between Ci and the whole history, so the intersection between Ci and the whole history, is the same thing as the intersection between Ci and that one J guy. Okay. So does that make it clear? You can see why this is a tree then, right? Because for every I, there's a corresponding J. So here's an example. We're going to do a couple of examples now. So here's a set of node clusters, and we're going to use clouds. I think I've used this a couple of times before, but basically we're going to use clouds to represent clusters of original graph nodes where the label of the cloud node corresponds to the node names from the original graph. So that means that, for example, this cloud node corresponds to the original graph nodes A, B, and D. Okay. And so we can, for example, consider BEH, which is this guy, and BDF, which is this guy. And what's the intersection is equal to B. And so we need to make sure that B exists on the path. So that basically means that from the perspective of those two tree nodes, the intersection does live on the necessarily unique path. There's only one path. It's a chain. it necessarily the intersection does live on the path between those two nodes. So let me ask you then. So does that alone, just looking at those two cliques, verify that the cluster intersection property holds, which is what your question was? And so you're correct in saying no, it doesn't. We need to check every pair. So let me then ask you this: is it the case that the cluster intersection property holds here? Looks like it. Raise your hand if you think yes. Raise your hand if you think no. Raise your hand if you think I don't know. Raise your hand if you are still checking. Raise your hand if you don't care. No. Raise your hand if you do care. I care. Well, we would have to check all of these guys. There are a couple of other examples, but the cluster intersection property does in fact hold because we check this one. Sorry, we check this one and this one. That one we already did. What if we check this one and this one? Well, there's A, B, D. There's no intersection. How about this one and this one? Well, the B is still there. So B we already know to be there. What about A, B, C, and B, E, H? Well, B is still there, and then this one. And then the only commonality is B and E now, and so it holds there. And then we can sort of do the same thing where we just do this and this guy. And B is the only intersection, and we know that exists on the path. And here, B is the only intersection, and we know that exists on the path. And then we have BD. So therefore it holds. So in a chain, we only have a linear as opposed to a potentially much larger number of things to check. But so it turns out that the cluster intersection property, I forgot about this part. So the running intersection property is another thing that we should verify here. And so the question is there an ordering of the nodes such that the running intersection property holds? Well, we could actually just go ahead and just order the nodes this way. So like, for example, this would be 1, 2, 3, 4, and 5. And so 2 is connected to 1. So when I is equal to 2, j is equal to 1. When I is equal to 3, there's A, B, C. So basically we need to have that the guy that 3 is connected to corresponds to the intersection of the whole history. So since A, B, C intersect with B, C, E, and B, E, H is equal to B, C, since this guy and this guy are common, the only edge that's possible at this point is the current edge that's there, from 3 to 2. And so then let's check from 4 to the whole history. So A, B, D. So A is an intersection, B is an intersection, but D doesn't seem to exist. So that means that we can summarize the intersection of the whole history with that edge, that does in fact exist there. And similarly, the intersection of 5 and the union of 1 through 4 is captured by the intersection of 5 and just 4, which is just BD. That's the whole intersection between 5 and the whole history. Okay, so therefore, both the cluster intersection property and the running intersection property holds. Question?
Is that also equivalent to say, to check the CIP? I can only check that for each A, B, C, for each one of them, they are forming a subtree.
Yeah, that's correct, and we will prove that formally. That is correct. Yes. The first thing we want to prove is this, which is that the running intersection property and the clique intersection property are identical. In fact, it's common to not even make a distinction between these two and just call them the running intersection property. But we just define them because we're trying to impart a strong sense of intuition. So how do we prove this? Well, it's actually not so difficult. So we're going to start by the clusters in their running intersection property order. And then we construct the tree the way that you would naturally construct the tree by connecting each guy to its corresponding j. So this is clearly a tree, right, because of the generative definition of a tree. And let's take any pair. We've constructed this tree, and you take any pair, and without loss of generality, let's just say that k is less than I. So I is the current one, and k lives at before. So that basically means that ck is a subset of the history, because remember, the history includes k. So that means then that the intersection of Ci and Ck is definitely a subset of the intersection of Ci in the whole history, because the history includes Ck. And that's equal to the separator S, which is the separator of Cj, which is S is a subset of Cj. So let me draw a picture to make sure this is clear. So we've got Ci here, we've got Cj here, which is the thing that's connected to, and we've got this tree somewhere back here, and somewhere back here is Ck that we've chosen, and there's some path between Ci. And then we have the whole history, which is all of this stuff here, and then we've got Si, which we can draw in green, which is the intersection of Ci and Cj, which is also equal to the intersection between Ci and the whole history. The whole history is equal to h of I. Right? So that basically means that we've got this guy being true. But on the other hand, notice that Cj is now one node on the path between Ci and Ck closer to Ck. Okay? And so then what we can do is then just sort of repeat the process by using this pair Ck and Cj if j is less than k, or sorry, k is less than j, or alternatively Cj and Ck. So basically whatever we just use, we use this guy again, and we don't know the generative order. It could be j is less than k or j is bigger than k, but we just sort of swap them so that whatever one takes the position of I becomes the last one, and then we have this whole history. And we do the same thing again. And so the reason why this works is because we found that this is an intersection, this intersection is a subset of that, but then we do Cj, which is the one of the guys closer with Ck, which we're going to find to be a subset of something else. And so we just keep going and we keep making the path one shorter and one shorter until eventually we get an adjacent cluster, which basically is such that it holds trivially. And so therefore, the cluster intersection property, meaning that the intersection of these two pairs lives within the path along the way. So then the converse is to do the following. So now we're starting with a tree, and we want to show that if the cluster intersection property holds, the running intersection property holds. So we can do a tree traversal. We can do a variety of different tree traversals, including like a depth first search or a breadth first search. So here would be a breadth first search. It's just an ordering of the nodes of a tree. It's breadth first search, so we do 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. Those are the orderings of the clusters in the tree that satisfies the clustering intersection property. Or alternatively, we could use a depth first search. Either one will work. Okay? And so then we've got these nodes so orders. And then we're assuming that the cluster intersection property holds. And we choose I, any position I, in the order that was chosen by the breadth or the depth first search. And then you take any k. Then basically, we're guaranteed by the cluster intersection property that Ci intersects Ck is a subset of equal to Cj for any j on the path between k and I. And in particular, that exists for the one that Ci is connected to. So like, for example, let's say that I is equal to 3. Let's use a smaller font here. It's not really a smaller font, a smaller. And let's say that k is here, maybe down here. And then j would be this one, right? Because j is the one that is connected to. And the idea of the clustering intersection property is that along this path here, the intersection of I and k exists on all of the nodes on the path between that, including j, which is this thing right here. Okay? And j is the neighbor in the tree. So that means that if we look at all the union of all previous ones here, that's also a subset of Cj. Right? That's just using the clustering intersection property again. And then we can just sort of factor out the common thing that we're taking in intersection and get this form, which is Ci intersect with the union of all previous ones is a subset of equal to Cj. And then since it's an intersection of Ci and some other stuff, which is a subset of equal to Cj, it's still a subset or equal to Ci intersects Cj. So we have this thing, which is almost what we want to get running intersection property. The other thing we need is to show that it's equal. In fact, we do need to show that it's equal. And we can get that by just trivially saying, oh, well, look, the reverse inequality holds. where when you take CI intersects CJ, that's always a subset or equal to CI intersects something bigger than CJ. And this holds why? Because J is less than I. And so it's included in that union. So that basically gives us the running intersection property. Okay, so the theorem is now proven. Any questions? Okay, so if this isn't clear, you can, again, review it again online, or rewind if you're watching it online. Just rewind and listen to it again. There's also, which is your question that was very prescient, was the notion of the induced subtree property. And the induced subtree property basically says the following, that if you're a tree of clusters, right, and you take any vertex, V, and you could take all of the clusters that contain that vertex, then the clusters that contain that vertex, when you sort of mark them on this tree, constitute a subtree. So here's a tree. Let's do another tree here. This is a complicated tree. So basically what this says, if we mark all of the vertices that contain, all of the clusters that contain a vertex, it necessarily has to be a tree. Okay. If it was the case, say for example, that there was a gap, say it looked like this and like this, that means that it's not, the induced subtree property does not hold. Okay. Was there a question?
Yeah, like back on one of the first review slides, you had that, I don't know what it was defined, it was some sort of like
tree decomposition, yes.
No, it was like a tree, but it was saying that when you take all the vertices that exist in the cluster.
Yeah, yeah.
So how was that, so this seems like that property.
Yes, in fact, it's property 3 of that definition. But now we're making it a little bit bigger. We're making it as its own definition because what we're going to see is that the tree decomposition property that we saw before exactly uses the induced subtree property. But there's a couple of other stuff that the tree decomposition needs, namely the vertex cover and the edge cover. But we'll get back to that. In fact, I'm about to show you that definition yet again. Okay. But the reason why we're doing this is for primarily pedagogical reasons, to sort of get a sense of all of these things by themselves and see how they're identical, as you'll see, and as this question earlier pointed out, that in fact the induced subtree property, the clique intersection property, and the running intersection property are the same. Okay. But which is nice because it means that we'll be able to show some additional things using any one of these 3 properties and make subsequent proofs very easy and simple, relatively simple. So first we need to show that the induced subtree property holds if and only if the cluster intersection property holds. And so let's say that assume that the induced subtree property holds. Any questions on what the induced subtree property means? Okay, so let's assume that the induced subtree property holds. So if we take any pair of clusters, and then every vertex in the intersection of these 2 clusters induces a subtree of T, right? So let's let me draw another tree, and we can picture that. So let's say here's a tree. Right. So take any pair. Let's take this one and this one. Okay. So we take the intersection, which is this guy, and then any vertex. And because the induced subtree property holds, anytime we take any vertex in the intersection, it necessarily is going to basically give us, like let's take a particular V. It might give us, say, this tree. Right? Now, why is it the case necessarily that there's a path? Because if it's in the intersection, that means that the vertex must live here, and the vertex must also live there. right? And so therefore, there has to be a path between those two vertices, Ci and Cj. Here's Ci, let's say, and here's Cj. Okay, so then we do all of these things, and then all of them have to have that property so all of these things, namely all of the vertices in the intersection of Ci and Cj. And so all of the vertices in the intersection of Ci and Cj must have this property that they exist on the necessarily unique path between these things. And that basically then gives us the cluster intersection property. Okay. So then conversely, let's assume that the cluster intersection property holds. And the way we do this is, let's choose any vertex V. This is the original graph vertex. And then let's just define the set of clusters that contain V. Okay. So what we want to do is we want to show that the clusters that contain V gives you a subtree. Right? What we have is the cluster intersection property. And so let's take any two vertices in this C of V set, the clusters that contain V. Because of the clique intersection property, we have that the intersection of these two clusters is a subset of CK, where CK is on the unique path between Ci and Cj. And we also have that V, which is that vertex, is in that guy, right? So that means that V always lives on these paths. And so when we have all of these paths for every one of these V's, and when we union them together, we're not going to get a cycle because we're unioning together paths on the tree. But then the key trick is that these paths are in fact a tree, meaning that they're connected. And the reason why they're connected is because if we take, let's say that we take, I think the picture is probably the best way to convince you of this. I keep drawing lots of different trees today. So let's say that this is all of the clusters that contain V. And so then the reason why it's connected is because when we say, for example, use, say, this V and this V, that's necessarily going to be connected via some other V. Right? So that means that all of these things are going to be connected together. And so that means that we've got not only a forest, but we actually have a tree. So that basically, I think, hopefully is convincing enough. So that basically means that the cluster intersection property, the running intersection property, and the induced subtree property are all identical. And we can use them freely. We can switch between them, whichever one you like at the moment to think about. Now, we're going to say that, you're going to see that each of these properties are critically important for a junction tree, which we're soon to define. So here's the definition again that you were asking about a tree decomposition. So remember, a tree decomposition is a tree where the nodes in the tree are clusters. These are the clusters. And we have to have an edge, a vertex cover, an edge cover, and this property, which we now see, property 3, to be the induced subtree property. Okay. So that basically means that we now know that whenever we have a tree decomposition, that the cluster intersection property and the running intersection property and the induced subtree property must hold. Okay, so all three of them must hold. Either one of them. In fact, we could replace property 3 with any of the other two, and this would be an identical definition. Okay, so let's just do a little bit of recap. Just a sanity check before we move forward. Yeah, question?
So the only difference between the cluster graph and a tree was that you need a non-zero intersection?
So in a cluster graph, we were pretty loose about the definition. We just said that it's basically a bunch of clusters, and there's an edge if there's an intersection between the two corresponding clusters. In a cluster tree, we dropped the requirement that there had to be an edge whenever there's an intersection. We just said that it's a tree, which means it's connected. Whereas the tree decomposition has these other properties. It basically means that this induced subtree property must hold, that the vertex cover must hold, and that an edge cover must hold.
All of these theorems have been just for cluster trees.
I can't say that. So go back and look at each theorem, and it says precisely what's needed for each theorem. So I mean, ask me about a particular theorem, and I'll answer the question for that particular theorem. So it's important. I mean, the statements of the theorem are pretty careful, I think, about what's required. And which theorem do you want to talk about? This one? And this is the definition. So this one basically says that the induced subtree property holds if and only if the cluster intersection property. So in both of those cases, it's just an if and only if condition. It says that if you've got one, you got the other, and vice versa. So in the case when the cluster intersection property doesn't hold, then the running intersection property doesn't hold, and then the induced subtree property also doesn't hold. They're identical. Does that make sense?
Well, I just felt like all these, they were being defined on, because all our examples were on trees, the cluster trees, and not on cluster graphs, so I was just wondering where.
Oh yes, everything we're talking about is a tree so far. I mean, except for the definition of a cluster graph.
Right,
But we saw some examples of cluster graphs last time where we removed edges and it became a tree. But a cluster tree, I mean, a cluster graph is obviously one for which these properties don't hold because these are not trees. A cluster tree is a tree, but it may or may not be the case that these properties, the running intersection properties, hold. And in fact, I think I forgot to state this, that basically we're going to collectively refer to these three properties as the running intersection property. Okay, so whenever I say running intersection property, we mean any one of these three, since they're identical. Okay? So this recap, I think, might also trigger some additional questions if there are any. So please ask. This is a good chance to ask questions as we go through. So remember, we want all of the original graph marginals. We want the marginals over all of the cliques in the original graph, in the not necessarily triangulated graph. Okay, we find an optimal elimination order, or we find an elimination order that's as good as we possibly can. We spend some time maybe running the heuristics, and we find a triangulated graph cover of the original graph. Or in other words, we find a triangulated graph into which the original graph can be embedded. Okay? And that basically gives us an easy way of finding the max cliques of the triangulated graph, which can then be used. We can marginalize out factors on the max cliques of the triangulated graph to get the marginals on the original graph cliques with computational cost equal to the size. It's equal to something that's exponential in the size of the largest clique in the triangulated graph. Okay? And so we define the notion of a decomposition of a graph and a decomposable graph and the corresponding factorization implications, namely the numerator of a product of max cliques and the denominator, which is a product of separators. The decomposable graph and a decomposition tree. We proved that triangulated graphs are the same class of graphs as decomposable graphs. We define the notion of a tree decomposition, which requires both a vertex and an edge cover and an induced subtree. Now I'm going to talk a little bit more about the idea of a cover in a second, if you're not familiar with those terms. We defined a cluster graph, which means that there's an edge whenever there's an intersection. A cluster tree, which is just a tree made out of clusters. And the clusters are the original graph nodes. And then we also defined the cluster intersection property, the running intersection property, and the induced subtree property, which we are sort of elevating and collectively referring to the running intersection property since they're identical. And if you look in the literature, by the way, most people they don't distinguish the three, they just say the running intersection property, and they only give the running intersection property definition. But I think that by looking at all three properties and seeing how they're identical, you get a much stronger intuition of what's going on in the running intersection property, which I hope is the case. Now the next definition we're going to talk about is the junction tree, which is a cluster tree that satisfies RIP. And it's an edge cover. Okay, any questions? So a junction tree, this is the definition of a junction tree. Raise your hand if you've heard of a junction tree before. So this is a really important construct in all graphical model problems. A junction tree is corresponding to a graph. If it exists, it might or might not exist, is a cluster tree that has the running intersection property over clusters, and where any two nodes, U and V, that are adjacent in the original graph are together in at least one cluster. So this is like an edge cover. Now, an edge cover in some sense implies a vertex cover if it's the case that the original graph is not disconnected, if there's not an isolated node. So for the purposes of this definition, let's just assume that the original graph is a fully connected graph, or is a connected graph, meaning that there's between any two nodes there's a path. Okay, so that means that an edge cover guarantees that we've got a vertex cover as well. So that means that a junction tree for a given graph is a cluster tree that satisfies the running intersection property over the clusters and includes all edges. Okay, so not all running intersection properties satisfying cluster trees need be an edge cover. Right? You could actually have, in fact, the definition of the running intersection properties in terms of vertex intersections. Right? You could actually have a running intersection property that has very few of the original graph edges in it, in its clusters. Like, for example, you could take a different graph over the same vertex set and construct a junction tree over that, and it wouldn't be, it wouldn't be a junction tree. You could construct a running intersection property satisfying cluster tree over a different set of edges, and it wouldn't have anything to do with the current set of edges. The other thing to note is that the clusters in the junction tree need not be original graph cliques. And why is that the case? Right. So the clusters could be max cliques on a triangulated graph. That's one thing. What if we? And another example would be, what if we just took the whole clique, right? What if we took the graph and put an edge between every two nodes? Would that be a junction tree? One big giant clique over all vertices. Is that a junction tree? Yes. Is that a useful junction tree? Probably not. But it's still a junction tree nonetheless. But that's another junction tree, which actually would be a triangulated cover, which wouldn't correspond to the original graph or cliques. So basically, a junction tree could have clusters corresponding to, either cliques or max cliques, or neither of the above. Neither of the above would mean, for example, when you have things that are much bigger than max cliques. As long as every edge is included in some cluster, we're fine. If the clusters correspond to the original graph cliques, or max cliques, then we call it a junction tree of cliques, or junction tree of max cliques. Now, one question for you to answer for yourselves is, when I say a junction tree of cliques, does that mean that the max cliques are not included in the junction tree of cliques? Can you have a junction tree of cliques that don't include the max cliques? What do you think? I'm not going to answer that. Maybe that's a homework problem. Okay, so here's some questions to answer. Some simple questions. So here's a graph on the left, obviously. And we have two cluster trees. So questions to answer are, is it a cluster graph? Are these cluster graphs? Yes or no? There's two answers to this question. There's one for the left graph and one for the right graph. So is it a cluster graph? Are these cluster graphs? Yeah, they are? So what about this and this? They're missing edges, right? So according to the way we've defined it, the answer is no. They're not cluster graphs, because cluster graphs say that there's an edge whenever there's a non-empty intersection. What about cluster trees? Are they cluster trees?
Can I ask a question about the cluster graphs?
Yep.
I think in a previous lecture, didn't you define the tree width of a cluster graph to be the size of the biggest clique minus one?
That was when we defined the tree decomposition. So the tree decomposition had a tree width. So in a cluster graph, we're not really talking about the tree width. We'll get back to that definition. Okay, so are these cluster trees? This is an easier question than maybe you're thinking about. So the answer is yes. Are these junction trees? So remember, junction tree requires that all edges are covered and the running intersection property holds. So we need to check, are all edges covered? I mean, I'll just do this one for you. So AB, is AB in a clique? Yes. Is AD in a clique? Yes. Is BD in a clique? Yes. Is BC in a clique? Yes. Is CE in a clique? Yes. Is CD in a clique? Yes. Is DE in a clique? Sorry, I'm missing the yes and yes. So all edges are covered. And since the right-hand side has the same clusters, then it's also covered. So we've got the edge cover property, but the question is, does the running intersection property hold? No, why does it not hold? What if we take the intersection of this guy and that guy? What's the intersection of those two? It's just B, and it doesn't exist here. So this guy is not a junction tree. What about the right guy? Well, we already know that it's got an edge cover. The only intersection to talk about is the intersection between this and this. And what's the intersection? It's D, and D lives here. So we're good. Yep, question?
Just a basic question. So these, the nodes, the cloud nodes, do they always must correspond with the max cleats of the original graph, the clusters?
Let me just go back to a slide to answer this question. Could have clusters corresponding to cliques, max cliques, or neither of the above. Okay. So the answer to this question is no, they don't need to necessarily correspond to max cliques. They could correspond to cliques. And the question I asked before was whether or not it's possible to have it correspond to cliques but not include the max cliques, and still satisfy the running intersection property. Or, now clearly, but on the other hand, they don't need to include any of the max cliques, because if you have a big giant completed graph, that's going to be a junction tree. And none of them, it doesn't correspond to any of the cliques or the max cliques of either the original graph or any sort of triangulation. And as we saw also before, if we triangulate by elimination, it might be impossible to get that triangulation. So it might be the case that it corresponds to clusters corresponding to the cliques of no elimination order of the graph, so no triangulation of the graph even. So it's very general. That's why I'm being very careful here to define a junction tree of cliques or a junction tree of max cliques.
Does the last definition also imply that the original graph is triangulated? If it's possible to find a junction of cliques.
Sorry, does which definition?
So the last one, if we have found a junction tree of cliques which correspond to original graph cliques, would that also indicate that the original graph is a triangle?
So you're once again prescient. Is it the case that you know this, or you're just imagining this?
Imagine.
You're just imagining? Well, then you should pat yourself on the back, because the answer to that is yes. That's very good. As we will see in another theorem, which we will look at in a bit, that they're identical, which is why we're doing all of this stuff. Because, I mean, just to answer that question, so the junction tree of cliques or max cliques and the triangulation of the graph, the junction tree is going to essentially be a property that always exists for a triangulated graph, and the junction tree is going to give us a really nice graph theoretic construct, i.e. data structure that we can use to actually implement inference on any graph using, as I warned you before, the same message passing schema that we use for general trees. And since we've got a junction tree, it's a tree. So we can use the same idea that we saw. So we already know how to do inference on trees. So we're, in some sense, like I was saying before, all exact inference is essentially a junction tree on a tree. Inference on a tree. Sorry, and in this case, it's going to be the junction tree. Question? Yes?
In general, that means
Um, I think I don't see why you would think that they're a subset. So like a tree decomposition can be formed by looking at a junction tree, and vice versa. Right.
Okay, I was thinking like, so junction tree doesn't necessarily have nodes corresponding to like leaves, but if you do the tree decomposition, the nodes in the tree decomposition would all be max. But not max.
There's nothing that said that. The only thing that the tree decomposition required was that all vertices and edges are covered, and that the induced subtree property holds. That's the same thing as the junction tree. The only difference that we've used here is that we're not saying that we want a vertex cover, but we've already qualified that by saying that we're assuming that the graph is connected. The original graph is connected. Okay? So, all right, so junction tree, no, yes. What about this? Junction tree of cliques. Well, the left one is easy. What's the answer to that one? No. It's not a junction tree, so it's not a junction tree of cliques. What about the right-hand side? The junction tree of cliques? Yes. Why? Because each one of those bundles are cliques. What about a junction tree of max cliques? Yes. Left-hand side is no. What about the right-hand side? Yes. Okay, so let's do a couple of more examples of these. The same kind of questions we're going to answer. So we've got this original graph. And the questions to answer are, is it a cluster graph? What about the left-hand side? Well, it should be clear that it's clearly not a cluster graph because, for example, it's missing this edge. And then if we go to the right-hand side, it's also not a cluster graph because it's missing the same edge. So therefore, the answer to this is no. Is it a cluster tree? Let's go to the left-hand side first. So is it a cluster tree? Yes, it's a tree of clusters. That's a very simple definition. On the right-hand side, a cluster tree? Yes. If we are missing an edge, like if we were missing that edge, then it wouldn't be a cluster tree. Okay. Okay, is it a junction tree? Now here's where it gets a little bit trickier. Is this a junction tree for this graph? So why not?
Nodes 2 and clusters 2 and 4 share k. The path does not.
Exactly right. Yeah. So there's k here and k here, but k is not in this one. So therefore, the answer on the left-hand side is no. It is not a junction tree for this graph. What about this? Is this a junction tree for this graph? The right-hand side. Hopefully everybody can see it. Okay, good. B here and 4, and there's no B here. So that means the answer to this is it's not a junction tree for either one. Whoops. It's not a junction tree. And so therefore the rest of the questions are easy, right? Is it a junction tree of cliques? No. Is it a junction tree of max cliques? No. Okay, what about this one? Is it a cluster graph? This one, let's do this. This one we know. No, right? No. Is it a cluster tree? Yes. We could do this for the rest of today's lecture. I can just give you lots of examples and ask you lots of questions. It would be a very interesting lecture. Is it a junction tree? Well, how might we do this? So like you start staring at this. Let's do this together a little bit. So let's just look at the induced subtree property, and that might be an easy way of doing it. So we look at A. Okay, so what's what nodes have A in it? So there's this one, this one. Okay, so A works, right? That's an induced subtree. What about B? So B, it's just these two, I think, right? Any more B's? So that works. What about C? Where does C live? C lives here and here. That's an induced subtree, right? What about D? D lives just here, I think. And what about E? Is there an E? E lives just here. Just one vertex. And that one cluster, that's okay, right? What about F? So F lives there and there and there. So that's an induced subtree. What about, is there a G? Oh yeah, there's a G right here. Is there any H's? Oh yeah, there's one H. I'm running out of colors. Okay, we've got this one last color here. H. Oh, and H, sorry, H lives here and here. I think that's everything, hopefully. Oh, no, there's I. Alright, I'll have to reuse a color. Oh no, actually I can use some other color here. So I is right here. That's a very similar color. Okay, I hope that's everything. But anyway, you can see that each vertex, each one of those colors was meant to represent the subtree induced by the vertex corresponding to that color. And so you can see that we've got all these colors, and each one of them is a subtree, and so therefore the induced subtree property holds, and so therefore the running intersection property holds, and all that kind of stuff. The only other thing we need to check is whether or not it's an edge cover, right? So the edge cover property, you can kind of see that by looking at like this bundle of vertices here, FAKCH corresponds to this guy here. So all of those edges, and basically you just go through every single edge and you check whether it's an edge cover. So it turns out that the answer to this question is yes. It is a junction tree. Is it a junction tree of cliques? No. Is it a junction tree of max cliques? No. So it's a junction tree, but it doesn't have to be a junction tree of max cliques. Okay. What if I change the graph a little bit and do this? So I've just added, all I've done is I've taken the graph here, I've added some edges. You can sort of get the animation effect by going back and forth. Isn't that cool? So, see, this is called manual animation. If this was PowerPoint, these things would be floating around and flying in and out and blinking and dancing and bouncing. But because we're using Beamer and PDF, I have to sort of get exercise while we're getting the animation. This is something we could also do all day, right? So what about this thing? Is it a cluster graph? No. Is it a cluster tree? Yes. Is it a junction tree? Yeah, the only worry is that if we added edges that sort of crossed over the boundary of, say, clusters, we'd need to recheck that. But it turns out that every single edge that we added lies entirely within one of the clusters that we already had. In fact, all we did, to be honest, to add these edges, is we just turned all of these clusters into complete graphs. That's all that we did to go from here to here. Let's do the animation effect again. You can see the edges that are being added. This is called structure from motion. The edges that are being added, you can see that this turned into a clique here. This turned into a clique here. Or sorry, a complete set, I should say. And this guy as well. Anyway, so getting back to this, is it a junction tree of cliques? No. Yes, yes, it is a junction tree of cliques. Is it a junction tree of max cliques? Sorry, let me just do this for a second. Yes. So let's just label them. So we've got this max clique here, which is this one. We've got this max clique, which is this one, HCI, human-computer interaction. And you've got this one, CDK, which is this little guy. And this big one, which is this one over here. And this one here, ABFK. Oops, that's not that one. That one. And then lastly, FGAB. So interestingly, I mean, you can see that when you start looking at the junction tree corresponding to a triangulated graph, there's a lot of overlap potentially, right? And so you can see that there's that just it's sort of I find it very interesting to look at these color sort of pictures on top of the graph corresponding to the cliques and the nodes in the junction tree, which is on the right. Yep.
Notation question. Some of the images you've been showing have square nodes that represent intersections.
Yes.
Why does this not have that?
Probably because I was lazy.
Okay.
Yeah.
Should they have?
It's
should we have them in our homework?
Well, I was going to include the definition of lazy. So definition lazy basically means professor forgetting or not having time or just being inept to actually be consistent and include the intersections on all edges. But in all seriousness, this graph, maybe it was distracting to have it, or it wasn't possible to lay it out in this particular way. I don't know. But you could, in general, I haven't even spoken about those square nodes. So the square nodes, basically, when you label an edge, we said once before that we label, I'm very glad that you asked that. So we label an edge with the intersection of the two corresponding clusters that edge connects. And the label corresponds to that intersection. So, and then usually use a square box for that. For example, in this one right here. So here's a graph. This is this graph that we've encountered before. So what do we remember about this graph? It's decomposable, it's triangulated, all minimal separators are complete, and so on. So does the running intersection property hold for this, obviously, tree of clusters? Maybe we should move on because this is going to take a bit of time, maybe two. But you should be able to look at these and then ask yourself, does the running intersection property hold? Does the junction tree hold? Does the junction tree of cliques? Does the junction tree of max cliques? And so on and so forth. And you readily have this decomposition tree at the top where you remember the property that the max cliques lie on the leaves. So there are the max cliques for you. Okay, a couple of other properties of junction trees that I think will give you a little bit more intuition about this notion of junction trees of cliques versus junction trees of max cliques. So basically what this property says is that we can take any junction tree, say of either cliques or max cliques, and we can create a new junction tree by essentially hanging off sort of tails from each clique, where each tail corresponds to a successively decreasing subset of vertices from the clique that's being hung off from. So I think the easiest way to see this is a picture. So let's say I have a junction tree where I have one cloud node, which is BCD, and maybe CDE or something like that, maybe ABC over here. So these are supposed to be clouds. So what this property says is that I can create another junction tree by, for example, hanging a tail where it's a subset. So this could be BC, and this could just be a cloud of C, and this could be a cloud of B. Right. So remember, these are all cloud nodes, right? So they're supposed to be clouds. And so the point is that doesn't change the running intersection property. Why? Because if we take any, well, certainly it hasn't affected the running intersection property between any of the original clusters. But then if we, for example, take, say, the intersection between, say, this and this, well, we know it lives here, because that's B, because this thing down at the bottom is a subset of the thing that we're hanging off of. And then it's a successive series of subsets going from the sort of root of the tail to, or the rump of the tail, whatever you want to call it, to down to the leaf of the tail. And why is that useful? Because if you, for example, have an ability to specify, say, a junction tree, and you have, say, a computational engine that can give you the marginals corresponding to the cliques, and let's say that you want a particular marginal over a subset of the variables in a particular clique. Like, let's say I really want for my application a marginal corresponding only to the probability of B. So I could then create another junction tree from this, using this trick, and get submarginals. And as you'll see, once we manipulate the junction tree into a form where the clusters correspond to marginals, we sort of automatically get the ability to do submarginals. Like, for example, B might correspond to a particular unary potential function for which we need the marginal over to do inference. So this is a really actually practical and really important property. Okay, so another junction tree manipulation step we can do to preserve the junction tree property is by taking neighboring cliques in a junction tree and we merge them together, or neighboring clusters. So the idea is that we merge these clusters together, we create a new cluster, Cij, and any of the neighbors in the original are of either of the original, basically, which in this case is Ci or Cj, basically become neighbors of this new merged cluster, Cij. And that preserves the running intersection property too, for the same reason, basically, because if you've got anything that involves that path, that one edge is no longer there, and so basically all intersections are preserved. So if you kept merging things together, eventually what we'd end up getting is just a complete graph. And that sort of is a guarantee that the complete graph is the junction tree, another way of guaranteeing that the complete graph is a junction tree. Or you could have these very, very big cliques. But obviously, if you merge cliques together, and they were originally, say, max cliques, the merged clique is no longer a max clique. It's something it's still a clique, or it's a clique cover, but it's no longer a max clique. So then the theorem that we have is that a graph is decomposable if and only if a junction tree of max cliques for G exists. Now here we're talking about a junction tree of true maximal cliques. And so this is a fairly longish proof, so maybe what we should do is take a break and come back and do this proof. So, okay, so let's get started. So I'm realizing that we're actually running quite a bit behind. So let me just state this and just emphasize how that this theorem and that it's important, and we're going to skip the proof. But basically, what it's saying is that the decomposability property of a graph is the same property as a junction tree of max cliques existing. Okay, and it's basically saying that all of these sorts of things, like the junction tree of max cliques and then triangulated graphs and every minimal separator is complete, are all the same property. And what's nice is that we have all of these things being identical, so the decomposability allows us to write the distribution in a particular way. The junction tree existing allows us to use a data structure that, as you'll see, which probably will be next lecture. So I'm not going to, like I said, this proof would take us a while. So I'm not going to prove it, but I do strongly recommend the complete proof is online in the slides, that you go through this proof. Okay. And another lemma is that a junction tree of max cliques exists if and only if a junction tree of cliques exists. Okay. This might seem like an interesting theorem, but as an exercise, the question for you is how do you get from one to the other? And then the question I asked you a little bit earlier is, if a junction, if you've got a junction tree of cliques, can it be the case that there's a missing max clique? Let me ask that. A question for you guys. If you have a junction tree can there be a missing max clique? Okay. And then the corollary we have, of course, is that the graph is triangulated if and only if a junction tree is clique. So we run the elimination algorithm. We're guaranteed that a junction tree of cliques exists, and thus a junction tree of max cliques. So elimination gives us away. Now, do all graphs necessarily have a junction tree of cliques? Do all graphs have a junction tree of cliques? No, that's exactly what this is saying. It has to be a triangulated graph for there to be a junction tree of cliques or a junction tree of max cliques. So the triangulated graphs are, the class of triangulated graphs are identical to the class of graphs for which there exists a junction tree of cliques or max cliques. Do non-triangulated graphs have junction trees? Yes. What about the big giant clique? The big giant completed graph. That's a junction tree. It's a cover. It's a node cover. It's an edge cover, and all that kind of stuff. But is it a junction tree of cliques or max cliques? No. So you can always construct a junction tree, but you always have to potentially add vertices in the same sense. You need to elevate the graph to the class of triangulated graphs before you're guaranteed for there to exist a junction tree of cliques or max cliques. Now remember, when we run the elimination algorithm, the max cliques are the things that we encounter as part of the elimination process. So that basically means that the size of the largest cluster in a junction tree is going to be equal to the size of the largest elimination clique that we encounter when we run the elimination algorithm, which is good, right? Because it means that we can actually, in some sense, if we find the minimal elimination order, the elimination order that yields the smallest max clique, that means that we've also found a junction tree that has the, at least potentially we found the junction tree that has the, a cluster that's small, smallest cluster. Of course, we need to know how do we get from a triangulated graph to a junction tree. And there's two ways of doing it. One way is to actually use maximum cardinality search. In maximum cardinality search, that same algorithm that told us if the graph is triangulated also will give us a junction tree. Or I should say, they will give us the cliques in running intersection property order. And from there, we can construct a junction tree by connecting Ci to the Cj that contains it. And that will be a tree of cliques that satisfies the running intersection property, and therefore it will give us a junction tree. And the only difference here is really this little bit of code. I sort of highlighted it on the next slide, but I accidentally highlighted a one that's a little bit too big. So that's the new code right there. So let's just look at it here. So what it's doing is saying that as we're running the maximum cardinality search, which, as you may remember, corresponds to a reverse elimination order, we've got to, let's assume it is a triangulated graph, so we never reach this fail condition here, so that never happens. And so what ends up happening is that we've got these elimination cliques, right? So Ci consists of the set of previously labeled neighbors, and Vi is the vertex that, when eliminated, basically completes the set of, or requires that the set of previously labeled neighbors is complete. And if it's the case that this set of previously labeled neighbors either shrinks in size or is the same size, which is this line here, then we add it to the list of max cliques in the running intersection property order. And then the very last thing we do is we add the very last elimination clique. Now the reason why we do that is because, remember, when we eliminate a graph, we saw that when we're doing it in forward case, the very first node that we eliminate is always going to be, that node and its neighbors at the time are going to be a max clique. So we always add that last one. Okay. And that becomes the last max clique in the running intersection property order. Okay. Now, but there's another way that to do this, which actually is the way I think it's more typically done, and we can essentially construct the max cliques in any, however we want. We could run the elimination algorithm, and that will give us the list of max cliques, as we saw before. And then once we do, we construct a cluster tree from the max cliques. Okay, so this is a cluster tree, meaning that there's an edge between two max cliques if there exists any intersection at all. So let's do an example. I don't think I have an example here, do I? Let's just do an example, a very simple example. So we've got A, B, C, D, and E. So we've got a cluster of A, B, D, C, D, A, and E, C, D. So those are the clouds of nodes. And then we form a cluster graph. So that basically means that we add edges if there's any intersection. So there's an intersection here, and there's an intersection there, and there's an intersection here as well. Okay, so because everything has some intersection. Then what we do is we label the edges with the intersection. In fact, we label the edges with the size of the intersection of the corresponding pair of clusters. So in this particular case, we would label this guy what? What would this edge be labeled? What's the size of that? It's 2, all right? And the size of this one down here is also going to be 2. Sometimes I have to remember that I don't have any way of pointing on this thing. So I'm like pointing on here, and you have no idea what I'm pointing at. So I have to draw an arrow to point. So what about this one? What's that one labeled? Yeah, 1. Okay, so we have now all of the edges labeled, and then we find a maximum spanning tree. A maximum spanning tree is something that's very, very easily solved using the greedy algorithm. We basically keep choosing edges as long as no cycles are created, and then the max spanning tree is going to be basically this. And that's going to be junction tree. Yep.
But doesn't this create a cycle?
Not if we find a maximum spanning tree. A maximum spanning tree is a tree, right? There's no cycles.
But if we talk just about this junction tree, can you still call it a junction tree? It's not a junction
No,
tree.
we said that we form a cluster graph, right? So the first thing we do is we form a cluster graph, which basically means that we add an edge whenever there's any intersection. Then we label the edges with the size of the intersection. Then we form a maximum spanning tree on the cluster graph, which leaves us with a tree, which has no cycles by definition. So that basically, the tree would be this yellow bit that I just highlighted, or I guess over there, down there probably, the yellow bit, right? So we can do that very, very efficiently in order E, V like V, which is much better than, say, for example, an n-squared prospect. And so, in fact, we have the theorem that a tree of max cliques is a junction tree, if and only if it's a max spanning tree on the max clique graph, which is the max clique cluster graph, with edge weights set according to the cardinality of the separators between the two max cliques. So that gives us a really nice and easy way. Now, of course, it's a really nice and easy way to find a junction tree. Now, it must be the case that the graph is triangulated, right? Because if the graph is not triangulated, then none of this stuff is going to work. Okay. Okay, so another little bit. So there can be multiple junction trees for a given triangulated graph. Whenever you have a shattering coefficient which is greater than or equal to 3, there are different ways of constructing a junction tree. Junction trees don't get confused or don't conflate the junction tree with the binary decomposition tree. Remember, the binary decomposition tree was a property of the fact that the graph is decomposable. Remember, where the separators are the non-terminals and the max cliques are the terminals of the tree, of the binary decomposition tree. The junction tree is different. Like a junction tree, might not have all minimal separators. You might have redundant separators. Like if I take this junction tree here, I could always repeat it by doing, say, for example, something like ABC, BCD, BCD, and CDE. Right, so there's a cloud, there's a cloud, there's a cloud, there's a cloud. And so here I've got a separator which consists of, let's do the separators in say green or something. So we have BCD. This separator, which is the intersection of these, is the same as the clique. It doesn't violate the running intersection property. So this separator is of size 2. This separator is size 2. But this one down here is of size 3, and in fact that corresponds to the intersection of the two neighboring clusters, which is exactly the same. But the running intersection property is preserved, so therefore this is still a junction tree. But it doesn't necessarily need to be the case that in a junction tree you have these minimal separators, like you have in a decomposition tree. So they're really different beasts. The junction tree, you have a little bit more flexibility. Remember, you can have these hanging tails of subsets of cliques, successive subsets of cliques. So the set of max cliques in a triangulated graph is unique, and the set of minimal separators is unique as well. But a junction tree need not be a tree over max cliques. It can exist over all sorts of things, as we've said. And if you construct a junction tree over max cliques, it will always have the same set of nodes and separators, but maybe there will be some different configuration. So even amongst the junction trees over cliques and, over max cliques, there's some variability there. Okay, so in the last few minutes, I want to talk a little bit about intersection graphs. So intersection graph theory is a whole other branch of graph theory, and this is sort of a graph theoretical or graph theoretic property of graphs, which like all graph theoretic properties of graphs are properties of graphs. But this is one that I think is particularly relevant and interesting. And we're going to see that, in fact, triangulated graphs are a particular type of intersection graph, where the underlying object is a tree. And this will, I think, strengthen our intuition between junction trees, triangulated graphs, and trees. Let's talk a little bit about terminology. So the idea of a set cover, this is just sort of for those who are interested in the sort of the, say the sort of this linguistic aspects of computer science theory. So a set cover basically is saying that you have a bunch of sets that must cover something. And the thing that's covered is not really listed, but it's really the ground set, or the set of sets must cover some sort of universal set. That's called a set cover. So you could call it a ground set cover if you want. A vertex cover is really like a set of vertices that must cover the set of edges. So the set of edges that are incident to the set of vertices must be such that when you union together those edges for a set of vertices, you've got all possible edges. And so you could sort of call it an edge vertex cover if you wanted to, because its edges are the things that are being covered by the set of vertices. And similarly, an edge cover is kind of like, it's a set of edges that cover the set of vertices. So you could call it a vertex edge cover. But then a clique cover is kind of like, we've already used that term a few times today. A clique cover is basically a set of cliques that cover the set of edges. So it's like an edge clique cover. So what that means really is that if you're an edge in the original graph, you must be a member of some clique, right? And so if you have a bunch of cliques, and if you're a clique cover, that means that every edge in the original graph is in some of the cliques in the list of cliques that you have. So it's called an edge clique cover, or just called a clique cover. So the nodes in a junction tree, therefore, we can just say, constitute an edge clique cover for the triangulated graph G. That means that any two vertices in the graph that are connected by an edge must live within some node on the junction tree. Okay? And so in some sense, we could reconstruct the original graph by doing the following. Let's say we've got a triangulated graph, and we've got a junction tree of max cliques. What we could do is we could just sort of put down a set of nodes. Let's say that these are a set of nodes. And then we could just say, okay, here are the set of cliques. Let's just color them in. Like say that's a max clique, and maybe that's a max clique, and maybe that's a max clique. This is a max clique. And when we do that, then basically we just complete all of the nodes. And so we constructed the original graph from the set of cliques by just making sure that all vertices inside of any max clique are mutually connected. So it's like an edge clique cover. Okay. So the last thing we'll do today is define an intersection graph. So an intersection graph, which will be the first thing we do next time, is a graph where each vertex of the graph has a corresponding set associated with it. Let's call it U sub v. And where the edge in the graph exists if and only if the corresponding sets intersect. So that basically means for every vertex in the graph, you've got a set. Right? Every vertex corresponds to a set of something. This is the vertex in the original graph. And what are these sets? Where do these sets come from? They're just there. They are there to sort of define the graph. And basically you're saying in an intersection graph that it must be the case that there's an edge between the two vertices u and v if it's the case that the corresponding sets intersect. And I think we need to end the class. Thank you very much. See you Wednesday.